Glass is one of the most extraordinary materials ever created by humans. It can last for thousands of years, is recycled almost indefinitely, and appears in every corner of modern life. But have you ever thought that all things of glass actually start from ordinary grains of sand? To create this transparent material, factories must heat sand to temperatures exceeding volcanic temperatures before passing it through relentlessly operating bottle-blowing machines, or transform it into streams of molten glass flowing over tin vats to create massive flat sheets of glass. So, is the glass manufacturing process really as complicated as you think? Let's simplify it with Mido Explained. Did you know that glass was discovered by accident more than 3,000 years ago? According to legend, a group of Egyptian merchants stopped to cook on a beach. They used blocks of sodium carbonate to prop up their pots on the sand. After hours under the heat of the fire and sand, they unexpectedly discovered a solid, transparent material and named it glass. For centuries afterward, glass was primarily produced by hand by artisans. It wasn't until the early 20th century that the first automated bottle-blowing machines appeared, allowing for the mass production of glass bottles at unprecedented speeds. Then, in 1959, the Pilkington float glass method revolutionized the industry further by enabling the production of nearly perfectly flat glass sheets on an industrial scale. First, let's take a look inside a glass bottle factory, where ordinary grains of sand undergo a truly remarkable transformation. Few people realize that the main component of glass is sand. But not all sand is suitable. Only sand with an extremely high silica content, sometimes as high as 99%, qualifies for glassmaking. This high-quality sand doesn't come from beaches or deserts. Instead, it's typically mined from massive open-pit mines. There, industrial explosives are used to break up layers of silica-containing rock before the material is collected, finely ground, and transported to the factory. This factory can receive and process up to 600 tons of silica sand per week. However, sand is not the only ingredient used in glass production. Besides silica sand, the raw material mixture for glassmaking must include approximately 15% soda ash and 10% limestone. Soda ash lowers the melting point of silica from around 1,700 degrees Celsius to a level suitable for industrial production, while calcium carbonate stabilizes the structure and increases the mechanical strength of the finished glass. If different colored glasses are needed, the plant adds specialized colorants. For example, cobalt oxide is used to create the characteristic blue color on some glass products. After all the raw materials are prepared and mixed in the appropriate proportions, they are passed through a screening system to remove any remaining impurities before entering the main production stage. After being screened, all the raw materials are transported to the mixing area via a long conveyor belt system. These conveyors can transport more than 15 tons of sand per hour and operate almost continuously without interruption. The mixture travels along the conveyor belt into a high-speed batch mixer. Here, each particle of the raw material is evenly dispersed to form a homogeneous mixture. The mixing process also helps to distribute the components more stably, creating favorable conditions for the melting stage to take place efficiently and consistently. The raw materials are then fed into a giant furnace heated to approximately 1,500 degrees Celsius using natural gas as the primary fuel source, a temperature even hotter than molten lava. Inside the furnace, the ingredients gradually melt and blend together into a homogeneous liquid mass. After about 24 hours, this mixture no longer resembles sand. Instead, it becomes a stream of molten glass that glows orange-red. However, the glass is still not ready for shaping. It remains in a molten state for several more hours during the refining stage. This process allows trapped air bubbles and remaining impurities to escape, helping the glass achieve the clarity required for high-quality products. Interestingly, these furnaces are almost never turned off. If the molten glass inside cools and solidifies, it can damage the furnace's heat-resistant lining, making restarting much more expensive than maintaining a continuous flame. The molten glass is then fed into a double-blow forming line, the most common method for producing hollow glass products. The process begins when the molten glass is cut into small blocks called gobs. These gobs are created from a continuous stream of liquid glass at a temperature of approximately 1,100 degrees Celsius. At this temperature, the glass is still soft enough to be easily shaped, but also dense enough to hold the desired shape without excessive deformation. Immediately after being cut, each gob falls precisely into a pre-molding die, where it prepares to undergo the forming process in just seconds. These gobs quickly flow into the preliminary mold. Inside the preliminary mold, a stream of compressed air is pumped in from above. The pressure of this airstream pushes the hot glass against the mold walls, forming an initial shape called a parison. At this stage, the parison resembles a hollow glass bubble with a preliminarily formed neck. Still glowing red from the high temperature, the parison is immediately transferred to the finishing mold for a second blowing. Here, a second stream of compressed air is pumped in, causing the softened glass to gradually expand until it fits snugly against all the details of the metal mold cavity. In just a few seconds, the complete shape of the bottle is formed. Although this process is extremely fast, all air valves, mold transfer mechanisms, and sensors are almost perfectly synchronized, with errors measured in milliseconds. Factories also tightly control the amount of glass fed into each mold and the air pressure during each blowing cycle. As a result, the glass is evenly distributed along the bottle walls, ensuring consistent thickness and minimizing weak points prone to cracking. Fresh out of the furnace, the glass bottles glow a brilliant red from the lingering heat. One by one, robotic arms move into position with precise, pre-programmed movements, gently lifting each bottle and placing it onto a moving conveyor belt. The conveyor belt then carries the glass bottles to the cooling area. Here, they enter a long tunnel where the temperature is gradually lowered step by step. This slow and careful cooling process helps stabilize the glass's internal structure, preventing cracking due to sudden temperature changes. This stage typically takes about 10 minutes or more. After cooling process, the glass bottles enter the quality control area. Here, a system of optical sensors and high-speed cameras continuously scans each bottle in real time. Any defects, whether cracks, air bubbles, scratches, or the slightest deformation, are detected immediately and removed from the production line. Next is the bottle mouth inspection. An advanced automated system rotates each bottle while optical sensors and mechanical probes work together to detect defects such as chipping at the rim, microscopic cracks, or even very small deviations in size. Only glass bottles that meet the standards are transferred to the packaging line. After passing the final inspection steps, the glass bottles are transferred to a fully automated palletizing area. Here, industrial robots use clamps and suction cups to lift multiple bottles simultaneously and place them onto pallets according to a pre-programmed layout. Depending on the product size, each pallet can hold from several hundred to over 1,000 bottles. Between the layers of bottles, the machine automatically inserts paper or plastic dividers to minimize collisions during transport. After stacking is complete, the pallets are wrapped in multiple layers of shrink wrap to secure the entire product and reduce the risk of breakage when forklifts move them. From here, the pallets are moved into storage or loaded directly onto trucks for transport to beverage, food, and pharmaceutical factories. Next, we'll visit a flat glass manufacturing plant where old glass isn't discarded but treated as a massive raw material. Piles of broken glass are scattered throughout the factory grounds, waiting to be returned to the production line. These glass fragments are collected and transported by conveyor belt to the mixing area, where they are combined with pure silica sand and additives such as sodium carbonate. Recycled glass typically accounts for about from 20 to 30% of the total raw material weight. This ratio significantly reduces the temperature required to melt the raw materials, thereby saving energy, cutting production costs, and limiting emissions. After the ingredients are mixed into a homogeneous mixture, they are placed in a fusion furnace. This furnace operates on the same mechanism as the furnace used in glass bottle making, so I won't explain this process further. After the melting stage, the molten glass is not shaped by blowing as in the production of glass bottles. Instead, it is passed through a float process, also known as the Pilkington process, the most optimal method for producing modern flat glass. In this process, a stream of molten glass is continuously poured onto the surface of a vat of molten metal, usually tin. Due to the difference in density, the glass floats on the tin surface and naturally spreads evenly into a flat layer. Under the influence of gravity and surface tension, the glass sheet self-balances, creating two parallel surfaces with very high flatness and smoothness. As it continues to move forward, the glass sheet passes through several precisely controlled temperature zones. Here, it is gradually cooled to prevent warping or the development of internal stress, helping to maintain its flat shape and transparency. As the glass sheets leave the tin bath, they continue to move along a long conveyor belt system. At this stage, precision becomes paramount. Pre-programmed robotic arms, programmed to precise parameters, begin their work. Using diamond-tipped cutting blades or laser tools, they cut the glass with very high speed and accuracy. Each cut is made precisely to create clean glass edges, avoiding cracks, chips, or surface stress. As a result, the glass sheets are prepared to the exact required dimensions. After being cut into individual sheets, the edges of the glass remain rough, often uneven or quite sharp. This not only affects aesthetics, but also poses a safety risk during handling. To overcome this problem, each sheet of glass is fed into a specialized edge grinding machine. Here, high-speed grinding wheels or continuously rotating grinding blades process all the edges of the glass sheet with evenly controlled force. This process helps to round the corners, refine the shape, and finish the edges with very high precision. The end result is a glass sheet with precise dimensions, a clean edge surface, and greater safety during handling, transportation, and installation at the point of use. Finally, the glass panels are lifted by robotic arms and neatly stacked on specialized racks. Between each panel, protective material is inserted to prevent scratches or damage from impacts during transport and handling. Once securely fastened, the entire stack of glass is transferred to the shipping area. There, they await loading onto transport vehicles for distribution to factories, construction sites, or stores worldwide. And that's the whole journey of transforming ordinary grains of sand into the glass products we use every day. From furnaces hotter than volcanic lava to robotic systems and state-of-the-art automated production lines, each sheet of glass or glass bottle undergoes a production process far more complex than many people realize. Which part of this process do you find most interesting? Leave your comments below and see you in Mido Explained's next videos.